Hello and welcome to all students. This is SYBSC class, SYBSC semester 4, paper 1, calculus 4. Now today we are going to start a new unit, unit number 3. The name of unit is beta and gamma functions and the applications of beta and gamma functions. So we are coming across two special types of improper integrals, beta and gamma functions or beta and gamma integrals, which plays important role to evaluate certain complicated integrals by handy techniques by expressing in terms of these integrals. Beta and gamma integrals are also used in double integrals, Fourier transform and Laplace transform. So first of all we define what is meant by gamma function or gamma integral, or we write the beta and gamma functions, or we also called beta integral or gamma integral. These two integrals are improper integrals, and they are the application of beta and gamma integrals are in double integrals. In solving while solving double integral we use these beta and gamma integrals. So first application is applications of these two integrals. So first application is in double integral. Second application is Fourier transform. Fourier transform, and third application is Laplace transform. So these two integrals are used in these three cases. So let us first we define what is meant by gamma function or gamma integral. So let us define first. We call it is gamma or gamma. Gamma function, or we may say it is gamma integral. So we write the definition. Write the definition. The definite improper integral, the definite improper integral, the definite improper integral integration over 0 to infinity e raised to the power minus t into t raised to the power n minus 1 dt is denoted by the symbol is denoted by the symbol gamma n and called as gamma n, and we read this symbol as and read it as gamma n. Gamma n are Euler's integral of the second kind or improper integral, or Euler's integral of second kind or improper integral. Or improper integral. So see here once again the definition. The definite improper integral, integration over 0 to infinity e raised to the power minus t raised to the power n minus 1 dt is denoted by the symbol gamma n, and read it as gamma n or Euler's integral of second kind or improper integral. So gamma n is equal to this integral. Okay, so let us write the integral now. Therefore, thus we write here thus we have the integral gamma n, it is equal to integration over 0 to infinity e raised to the power minus t into t raised to the power n minus 1 dt, comma, here condition on n is n must be strictly greater than 0. So this is called as a gamma integral, or we may say it is gamma function. Okay, so integration is gamma n is equal to integration over 0 to infinity e raised to the power minus t raised to the power n minus 1 dt, n greater than 0. Now secondly we see the properties of this gamma function or gamma integral. So this gamma is a function of n where n is greater than 0. Okay, so second we write here the properties of gamma function. Properties of gamma function. Properties of gamma function. So first property of gamma function is, we write here gamma 1 e has value 1, gamma 1 is equal to 1. So let us try to prove this property. Write the proof. As we know the definition of gamma integral, gamma n is equal to integration over 0 to infinity e raised to the power minus t into t raised to the power n minus 1 into dt, where n is greater than 0. So this is the definition of gamma function, and in this definition we put n is equal to 1. We put n is equal to 1. So if I put n is equal to 1, then this implies gamma 1 is equal to integration over 0 to infinity e raised to the power minus t. So wherever is n, we put, instead of n we put 1. So t raised to the power 1 minus 1 dt. Okay, so here 1 minus 1 is 0, t raised to 0 is 1. Therefore what we left is 0 to infinity e raised to the power minus t dt. Okay, so now solve this integration and see what is the value of gamma 1. It is equal to, so integration of e raised to t is e raised to t minus e raised to t upon minus 1, and this is integration over 0 to infinity. So minus sign we take outside, minus 1, and inside the bracket e raised to the power minus infinity minus e raised to the power minus 0. Okay, and e raised to the power minus infinity, the value of e raised to the power minus infinity is 0, minus into bracket, this is 0 minus the value of e raised to the power minus 0 is 1, and so finally we have plus 1. Okay, so therefore the value of the gamma 1 is equal to 1. So this is our first property of gamma function. The value of gamma function at gamma n at n equal to 1 is 1. Okay, so let us see the second property. So second property of gamma function. Second property is, that property is called as a reduction formula for gamma function. Reduction formula for gamma function. Reduction formula for gamma function. Okay, and that reduction formula is gamma n plus 1 is equal to n into gamma n. Gamma n plus 1 is equal to n into gamma n. So let us try to prove this reduction formula. Okay, so it is very simple. Write the proof. Okay, so now we write the definition of gamma n plus 1. So gamma n, the definition of gamma n is known to us. We write definition of gamma n plus 1. So here gamma n plus 1 is equal to integration over 0 to infinity e raised to the power minus t into t raised to the power n dt. Okay, so this will be the definition of gamma n plus 1. So if I put n plus 1 in the definition of gamma n, okay, so now this right hand side, now just try to simplify this right hand side, and on the right hand side we have exponential function, and the second is a algebraic function. Okay, so to solve this integration, what we have to do is we use integration by part. That thing is known to us. Use integration by part integration by parts. Okay, so left hand side as it is, I will write from this sign is equal to, this integration is equal to, so integration by part is here. So this is our algebraic function. We take first function, and exponential function we take as a second function. Okay, so first function as it is into integration of second function minus integration of first function into derivative of second function, sorry, integration of 2 so we directly write the integration by part here. See here, t raised to n e raised to minus t upon minus 1 over the integration is over 0 to infinity minus integration over 0 to infinity derivative of first function n into t raised to the power n minus 1 into integration of the second function is e raised to the power minus 1 upon minus 1 dt. Okay, so and it is equal to the value of this term is 0. Okay, so this minus and this minus and it becomes plus, and n is a constant, take outside, and integration over 0 to infinity, and it is e raised to the power minus here it is e raised to the power minus t. So what is left is e raised to the power minus t into t raised to the power n minus 1 dt. It is equal to, this is n into the integration is gamma n. So in this way we have proved the second property of integration, and that property is the value of gamma n plus 1 is equal to n into gamma n. Okay, so this is our second property of the gamma function. Okay, now here we write some note for the gamma function. We write some note. Note is that if n is positive integer, if n is positive integer, then gamma n plus 1 is equal to n into gamma n. Okay,
कुठं आईस्क्रीम मम्माने खाऊन घेतली.
it is equal to n into, so can we use this same property for this gamma n? Yes, we can use, and it is n minus 1 into gamma n minus 1. Okay, again we can use the same property for this gamma. It is equal to n into n minus 1 into n minus 2 into gamma n minus 2. Okay, so in this way we use this property, and finally we get the thing is n into n minus 1 into n minus 2 dot dot dot. Finally we will have 3 to 1 into gamma 1, but gamma 1 is 1, and it is equal to n factorial. This product is nothing but n factorial. So finally, therefore we have a new result for gamma function, and that result is gamma n plus 1 is equal to n factorial. Okay, is equal to n factorial. Gamma n plus 1 is equal to n factorial, or we can write gamma n is equal to n minus 1 factorial. So both results are same. Okay, here only okay, here n is greater than 0, strictly greater than 0. Okay, so now let us go to the third property of gamma function. third property of gamma function. Third property of gamma function, gamma 0 is equal to infinity. Okay, so we can prove this property very easily. So let us write the proof of this property. Let us write the proof of this property. We know that proof we know that the property of gamma function, gamma n plus 1 is equal to n into gamma n into gamma n, and therefore from this relation we can write gamma n is equal to gamma n plus 1 upon n. Okay, put n equal to 0. I want gamma 0, therefore put n equal to 0. So left hand side becomes gamma 0, and it is equal to, it becomes a gamma 1 divided by 0. Okay, so gamma 1 is 1 upon 0, and the value of 1 upon 0 is infinity, and therefore gamma 0 has value infinity. Okay, so in this way we proved the property gamma 0 equal to infinity. And okay, so this is so today we have seen the definition of gamma function or gamma integral. It is improper integral, and we have stated some properties of gamma function. And this is the end of our today's lecture, and thank you for paying attention. Thank you very much.